Fantastic. Thank you very much, everybody, for coming to this year's Data Club Data Expo event. My name is Maxwell Salvador. I'm president of Northeastern's Data Club. And this semester, we had a lot of fantastic projects that we're going to be presenting today. Mainly, we have two programs that we had at the Data Club this semester. We had the Snowball program, which helped students come up with data science project ideas and then develop those fully. And then we had a vaccine data challenge, which we launched earlier in the semester. And then we had students try to develop, solve the problems of distribution networks for vaccines across the United States, which is something that we're seeing right now as we're trying to get vaccines to everybody, and is something that's very interesting to see what all these students came up with. The quick agenda for tonight, what we're going to be going over is, right now we're just going over a quick event introduction. Then we're going to be starting with the Snowball projects. We have 5 Snowball projects that we're going to be presenting, and I'm going to give the order very briefly. Then at 6:45, we're going to start with the vaccine projects. Again, we have 5 of those. We have 3 undergraduate projects and we have 2 graduate projects. And then once those finish up, we're going to be going into the vaccine results. We're going to be going into the results of the presentations of the projects and to declare the winners. All winners were declared prior to this presentation, so this is kind of a formality just to kind of give you guys an idea of the amazing projects that each of these students developed. Regardless of the results, I'm so happy that everybody submitted their projects, and to see what everybody submitted. It was possibly beyond anything I expected students to submit, given the project scope. So really happy that you guys all took part in this, and really happy to share with you the results. So without further ado, we can get started with the event. A quick introduction to Data Club for those of you who may be new. Our mission at Northeastern Data Club is to promote data literacy in all disciplines. And that's really the core of what Snowball and the Data Challenge tried to do this semester. We wanted to really bring in students who may not just be from Corey or data science, but maybe from a more health science background, more business background, and try to introduce them to these core concepts of data analytics and guide them through developing their own data science projects or competing in a competition like the one we launched this semester. As I mentioned, we're going to be going over the Snowball projects. That was a semester-long project the students worked on. And then the data challenge participants, who compete to develop visualizations and analytics to show how to properly distribute vaccines across the United States for COVID-19. Without further ado, let's get into the Snowball presentations. Starting it off is a student named Marco. He's going to be presenting his project on detecting anomalies in offshore oil wells. Really quick, let me just give the presentation over to Marco, a co-host. And Marco, you're all set. Take it away.
Let me just share my full screen. Yeah, that'll work. So, yeah, hello. My name is Marco Tortolani. I am a freshman at the Corey College of Computer Science, majoring in data science. So this club is kind of fitting for me. And my presentation today is on detecting anomalies in offshore oil wells. A little bit of background. When trying to, in the start of the semester, when trying to see what kind of projects we want to go into, I'm like, oh, maybe I want to do something about like energy, or maybe about like airplanes, something in industry. So Max, and that didn't really catch on, but Maxwell came forward to me. He's like, I found this one particular data set by these researchers that is studying active multivariate data produced by offshore oil wells. And when he proposed to me, I looked at it, and it's literally 1,984 CSV files that he handed me. And I'm like, Maxwell, you're trying to kill me. So, but eventually I warmed up to it. I started reading the documentation, and it was very interesting. And I decided I'll take this on. The issue with doing oil data and doing studies on oil on offshore oil wells is that there's not much publicly available information on this, not many publicly available data sets. But I believe it was 2018, 2019, some researchers working for Petrobras, a Brazilian oil company, made a study called the 3W data set on 3 different offshore oil wells. And they studied 6 different points. which were 3 temperature values and 3 pressure values that were and this was pressure and temperature data collected from these oil wells. Oh, my bad. Let me just go back. And this is data that's actively collected in these oil wells. Those 6 values, it's measured in 1 second interval. So every second you're measuring data, measuring 6 points of data, measuring 6 points of pressure and temperature data. And that I added it up and it goes a total for 14,091 hours of just every second data collected. And it's a data set that gets really overwhelming really fast. But at least I kind of got to display here how it's kind of distributed. There's the real data sets, the simulated data sets provided by the researchers to kind of round it out, and then the drawn data sets that were handmade. And you kind of see what type of errors they're trying to propose. They have the normal wells that suffer from flow instability, spurious closure of DHSV, which from you see at the bottom left is like the little ball that blocks the well, severe slugging, abrupt increase of dirt creation within the tubes, rapid productivity loss, quick restriction in the surface, scaling in surface exponential surface, like what comes out the surface, and then hydrated production line. And from there, you have our classes, and we can start approaching this from a machine learning point of view. So moving forward to a methodology, first of all, first issue was managing the almost 2,000 CSV files. And you start that out by importing the data set, separating the data set depending on which error type it is, separate by analysis type, which is well simulated or hand drawn, which is important if you want to kind of isolate a certain type to see what's more real, what had to be filled in. Then we removed NA and frozen data, which if you can see at the bottom left is provided by the Journal of Petroleum Science Engineering. You kind of see that for the pressure at the bottom of the well, you have updated time series data that is constantly measured. Then in the bottom row, you have pressure at the surface, which is constantly produced data. Yet in the middle, you have temperature, which is kind of frozen. And this happens a lot in oil wells where you just have either temperature pressure values that aren't measured or just fail on the spot. So we kind of really have to account to that because traditional machine learning methods really don't like that at all. We then split it into evenly timed data, which is I split it into 60-second intervals because I felt that that would be enough that I could accurately plug it into a machine learning system without it like taking years to train, and then put that into a dictionary. Now, to the next step of managing the time series, you have to take this this set of data and put it in a time series format. So instead of just like the iris data set where you have flower length, petal width, points of data, in a time series you have a row of data, and with multivariate time series, you have many rows of data that kind of overlap, and that all makes up 1 point. So you can see in the top right, I kind of illustrated it, that 1 point, that's 60 seconds. That's 60 seconds with a measurement taken every second. And that's of dimension 6. So that's 360 different data points that all go into one quote unquote point into the machine learning. So you kind of understand that this problem gets really big, really fast. And when you start trying to actually run this kind of stuff, it takes a fair amount of time. Then cleaning, which I guess I already addressed previously, which is kind of managing the, making sure that all the variables are okay and getting in the right format, the right time series format to plug into ML. And then with ML, one of the main issues with ML, it's like a kind of new thing, and not new, but it's been like an ongoing like issue at ML, is how to manage data set, how to manage time series. Because as you see in the bottom right, you have two graphs that are fairly similar, but there's distance between them. And the machine learning, traditional Euclidean methods of machine learning, like K nearest neighbor, will say those are different graphs, even though we see with our eyes that no, those are the same graphs, just kind of shifted. So that's when we implement something called dynamic time warping. Dynamic time warping is saying, okay, instead of going straight up or down, or go to the X, go straight up and find the distance with that, from the X within a window, find the nearest Y, and then find the nearest y, and that's going to be the distance. And that helps a lot because it makes it a lot more straightforward for the machine learning to understand that, okay, these two are very similar graphs. They're just out of time. They're just out of sync. So I shouldn't put that much against it compared to Euclidean, where it's like, I don't recognize what's going on. And then finally, once we get our visualization, once we put it into a DTW format, dynamic time warping format, then we can plug it into a more traditional, like, for example, a k-nearest neighbor machine learning, like I used in this project, and create our visualizations appropriate. So moving on to the results. The results, I think I came out with two important results here, two at least like learning results here. First of all, I would like to take a look at the right, which is I ran a k-nearest neighbor classifier with k equals 3 on a data set that was 8,454 time series, which is essentially 6 time series, 60 seconds each of dimension 6. And if I just move over my little zoom window, we'll see that the weighted F1 score, which, as I explained in the top left, that is the most accurate way that we measure these results, since it takes into both the precision and the recall, and it takes into account how much input of each variable, the support of each variable, the support of each class when it's giving the result. So with a weighted F1 score of 0.85 and an accuracy of 0.86, 85% and 86%, I at least see that from just simply putting the time series, dividing it into minute intervals, using, instead of Euclidean, switching it to a dynamic time warping measurement system and plugging it into traditional k-nearest neighbor learning, we can actually get fairly good results towards being able to detect whether there is an anomaly in an offshore oil well. Even though the original data set was about 800,000 point time series of these, minute time series, I could only do 8,500 on my computer. It would literally take roughly 8 hours to run this. K-nearest neighbor is notorious for not scaling well with bigger data sets. And when each point is 360 data points, it really does not enjoy that. So I'll explain this more in the next slide, but we kind of see where moving forward in this project we kind of want to approach. And I was very also happy with these results because compared to I believe one other study that was done on this, where they kind of say, okay, its classes are 0 or 1, and we can see either the well is fine or there's an error in the well. This is fair. This ML method is fairly good at determining exactly what error is occurring, and if there is not just if there's an error occurring, what error is occurring, which that information gives a lot of value to those who run the wells, that allows them to more directly address and manage the problem. And lastly, from results in the bottom left, this measurements I did in a sub portion, which is 0.1% of the total data set, which is what I could run without having, which is how I could run this 50 times without like it taking forever, is that I kind of got to see, okay, what if I use different k variables? What if I increase the k variables? So with that, I got to see that a k equals 1 actually gives me the best results, not k equals 3. I did a measurement on k equals 1, but it's not usually advised for you to use k equals 1. We can see as we increase k, our F1 score starts going down. What's at absurd levels of k, like k equals 49, it starts going to below 0.5, but even at moderate levels of k, or k as like 7 or 9 or 11, we still get pretty good results. And this kind of introduced me to the balance of a low bias versus a low variance. And bias versus variance, that's a big deal with choosing k, and how much you want your machine learning, your k-nearest neighbors how you have to compare whether you want it to be a lot more accurate with your data, or whether you want it to be more accepting to new data and get a more rounded approach. So that's another kind of outtake that I got from this. When So to consider whenever I want to move forward with K nearest neighbor projects. And from that further work that I believe that I have to do, or looking ahead, I believe that one of the first things that I should do with this method, because even though it's effective, it does take a lot of computing power that my computer just couldn't handle if I want to keep pushing this forward. So this would be a great opportunity for me to look into either connecting to AWS or Azure in order to kind of rent out cloud computing and kind of, as far as I can, use the extra computing power to push this forward and see what other see if I can handle if I can handle greater portions of the data set, and B, if instead of measuring every 60 seconds, measure every 360 seconds, measure every hour, and see how that different time inputs affect the project. Secondly, something that if I really want to get into the stats of it, I could, this is kind of really looking ahead. But the issue with stuff like oil wells or stuff like flights or stuff like rocket deployment is that you'd much rather have a false positive than a false negative. So when I have to measure whether I want more bias or more variance, how accurate I want this to be, I should really try to make a program that, or make an analysis that, a model that even if it's unsure, it will alert me so I can take the appropriate steps, rather than if it's unsure. I want a model that when it's unsure to take it on the safe side. And hopefully I can integrate that as I move forward. And lastly, looking ahead, something that I should take on is unsupervised learning method. K nearest neighbor classifiers, even with dynamic time warping, are taking into account that you have your data set, and your data set is has preset classifiers and is put into like its appropriate buckets. But when you move to bigger data sets and data sets like offshore oil well anomaly detection, that often doesn't have as clear results or clear inputs all the time. Stuff like isolation forest and unsupervised learning mechanism would be a lot more fitting to handle both the scale and the type of project that I'm trying to go through with. Like as you can see in the bottom right, where more surface level differences in the data set are quickly determined to be anomalies. Meanwhile, the deeper and more specific you get, the more likely that it's just a coincidence. That's kind of how isolation forest works. And it'd be good to start implementing machine learning methods, unsupervised methods that are like kind of designed for this kind of anomaly detection into these projects. The only issue is that I'd have to myself figure out how to implement the dynamic time warping that I was speaking about earlier, and integrate that into methods such as isolation forest or light GBM. But that's would be kind of moving forward with the project. And with those three things, I don't know how much time we have left and how we're doing. But if anyone has any questions, or if anyone wants to reach out, if anyone has any curiosities about the process, the code, anything at all, please contact me. And thank you for watching.
That was absolutely fantastic, Marco. I worked with Marco pretty closely on this, trying to help him, but he kind of took hold of this project and went for it. This data set, I can attest, was like
yeah, no, I appreciate Maxwell. I kind of just sat and called with me sometimes, is like step by step, slowly. Like
this was a really hard data set to work with. Super proud of you, Marco, for working through that. It is very impressive. I wish I could open the floor to questions. We got to keep moving though. We're running a little short on time. We're going to be posting this presentation on our socials, out to our email chain. And we're going to be including all the emails of everybody who presents. If you have any questions, please reach out to Marco or anybody else who's presenting today. All right, sweet. Thank you very much, Marco. All right, next up is Krish and Ayan to present NFL betting model. I gave you guys co-hosts, so whichever one of you wants to present, you go for it.
Ayan, do you want to present? You're on mute. You're on mute.
My fault. Yeah, give me 1 second.
Sure.
Share screen. Oh my gosh. Okay, sorry. I'm not super good at using Zoom, but present. Hi everyone, my name's Ian, and this is my friend Krishanu, and our project was working on creating an NFL sports betting model.
Yeah. So as Ian and I have found out through personal experience, the world of sports betting is volatile and unpredictable. However, by finding variables from past games that can help us, that can be most indicative in predicting the outcome of future games and applying them to classification machine learning tasks, we strive to maximize profits from betting on the NFL. And we decided it was an important problem to tackle because it could prove monetarily beneficial to us. In addition, working on this problem would help us learn more about how sportsbooks accurately set odds and lines to turn a profit.
So for our first visualization that we created a pretty simple line plot just detailing the differences between the ELO rating of teams, which is essentially like a Z-score assigned to every football team based on, like how strong of a team they are. So the ELO rating of every team that plays against each other versus the margin of victory. So as we can see from the line plot, as the ELO ratings of teams increases, so say one team is significantly better than another based on their ELO ratings, the margin of victory of that team tends to increase as well.
Yeah, so our second visualization is kind of in the same vein in that we have QB ELO difference on the x-axis, which is one of our feature variables. And we want to see how that had an effect on the favorite covering the spread. So to people who don't know what those words mean, a spread is like kind of like a predicted margin of victory that the sports book would set. And then if a favorite beats that predicted margin of victory, they've covered the spread. And so this is a conditional density plot. And as you can see, as QB ELO difference goes up, there's a slight, very slight increase in the number of the percentage of favorites that cover the spread. So moving on to our methodology. First, we had to acquire the data, and we did this in a variety of ways. First, we used various websites such as 538 and some free GitHub repos we found online. And then we utilized web scraping with Beautiful Soup on other websites to scrape other feature variables, potential feature variables that we thought could have an impact on the outcome of football games. And then once we had this data, we put into data frames using like pandas in Python, and we cleaned the data. So this included removing weeks that we thought would like not be relevant to the data. So for example, we removed all week 17 data from our sets because traditionally in week 17, some teams sit their players, so they could be harder to predict with one standardized model. And this is just one example of like a lot of cleaning we have to do. And then we utilize one-hot encoding, which is kind of a strategy to create quantitative variables, a bunch of them from one categorical variable. And we did this with a variable called super home advantage, which we looked into. And then we standardized the data to make sure the scaling was appropriate for all the variables. And then finally, we used recursive feature elimination to select the features that would be most important to or had the most impact on our target variable of favorite cover, which is the favorite covering. Yeah, that's what we did up until the results.
Yeah, so as Krishanu detailed, we did a lot of different pre-processing, and finally it came time to, take the aggregated data set that we had created to essentially run it on different classification models. So we created a dictionary object of 5 different classification models, like k-nearest neighbors and a linear support vector machine. A couple of others as well. And so we also created then this function that ran through, scaled all the data, split it into training and testing sets, and then created like a classification report detailing the accuracy and precision of each of the models running on our data. And what we found was that our linear support vector machine, or linear SVM, it had the highest yield percentage, or testing accuracy, sorry, of 55%, and the training accuracy was around 55% as well, which is indicative of a balanced fit. And this number might seem low, but within the context of sports betting, through the various research that we did, we found that one needs to hit on, or needs to convert basically, or predict 52.4% of their bets in order for them to break even in the long run. So if given this magic number of like 52.4%, our model is currently predicting at a rate of 55%. So we do have the potential to, make profit over time, but we definitely would want to maximize this percentage, this testing accuracy in the future. So in order to do this, so we did attempt to create an LSTM model, which is essentially like it's called a long-term short memory, or long short-term memory. Sorry, my bad. That model, it essentially takes into account the fact that our data is time series data, which, because like it's essentially every football game and the data from every football game from, I think, like 1979. So taking into account this time series data, we wanted to, these LSTM models have these things called memory cells, which can remember a specified amount of data from before to predict the output of the next, the next game. So we ran into a problem of an exploding gradient in creating this artificial, this LSTM model, which is a type of artificial recurrent neural network, basically. So because of this problem of the exploding gradient, we weren't able to get accurate test results. But this is one thing that we want to pursue in the future in order to maximize our accuracy.
Another thing we could do in the future is, so for our original a problem, we want to try to tackle it as if like it was a classification problem. But in the future, we could look to using regression machine learning models as well, where the model would predict the score of each team. And with the score of each team, we would have like a prediction for the margin of victory with a reasonable accuracy. And then using that, we could compare it to the spread and assign a percentage of how confident we were that the favorite would cover the spread. And I've included an image of like a different model I found online, and this is how they were doing it. So we could try to do what they're doing as well. Thanks for listening. And I think we're short on time, so no questions, unfortunately, but thank you again, everyone.
Thank you, everyone. I really appreciate it.
Awesome job, guys. Yeah, unfortunately, no questions. Again, we're going to be sending all the information, and then we'll be taking questions through email or through any social media that you guys would like to see. We'll be doing also spotlights for all of these presentations in the future, so be sure to message us and we can get those questions to those guys and they can answer anything you want to know. Next up is passing versus rushing in the NFL by Chloe, Garen, and Vivek. Who is going to be presenting that, so I can just give you permission to present?
Yeah, I was gonna share my screen.
All right, go for it.
All right. Is that working? Can you guys see that?
Yep. All right. Hello, everyone. I'm Chloe Goslin.
I'm Vivek Devakar.
And I'm Garen.
And we're going to present to you our project on passing versus rushing in the NFL. So using 2019 regular season play-by-play data, we analyzed rushing versus passing decisions and success for the NFL teams. And we primarily used Tableau. Also, our data is from Ryurko on GitHub, and we also used NFL.com. So I looked at which teams should have focused more on passing or rushing in 2019. To do so, I completed the following steps. So first, I compared the pass WPA to the rush WPA, and WPA means when probability added. Next, I compared the yards gained from passing to yards gained from rushing. And then finally, I compared the pass attempts to the rush attempts. And so from this, team by team, I was able to analyze whether they should have passed more or rushed more. So I've picked out just 3 cases from the NFL, the 32 NFL teams to discuss with you today. But I have data on all 32 teams if anybody wants to shoot me an email after asking any questions about a particular team. So first we'll look at the Baltimore Ravens, who had the best regular season record in 2019 with an 875 win percentage. So the Ravens had a rush WPA of 211.6, which was the highest rush WPA of all teams. Meanwhile, their pass WPA was 90.5, which ranks only 8th in the league. So this shows that Ravens accumulate more win probability from rushing than passing. In fact, rushing accounts for 70% of their total WPA, which is a high proportion in comparison to the other teams. So on the left graphs, the top graph represents the pass WPA, with the Ravens highlighted in the bottom graph is the rush WPA. So you can see these results as well. So next we'll look into the yards gained, which is the middle visualization, indicated by BAL for Baltimore. So the Ravens gained 3,317 yards from rushing, which is the most yards gained from rushing of all teams in 2019. And they gained 3,325 yards from passing, which ranks 28th of all 32 teams, which is kind of fascinating considering they had the best record, but and also ranked second in total yards, but had almost one of the last few in yards from passing. So this can also be seen in the visualization. So the orange signifies the rushing and the blue signifies the passing. So the Ravens clearly have an exceedingly large proportion of rushing yards gained, especially in comparison to all of the other teams. And so finally, we'll look at the attempts, which is the right graph. And again, the orange is for rushing and the blues for passing. So the Ravens had 600 rush attempts, again, most in the league. And they had only 469 pass attempts, which was last in the league. So clearly they prioritized their rush attempts and it worked for them considering they had the best regular season record. And for reference, like on average, teams had 41% of all attempts as rush attempts, but they had 56%. And so in conclusion, like the Ravens are an example of a success story. They prioritize their rushing as they should have. And so next I'll look into the Colts. So in terms of WPA, the Colts had a 73.2 pass WPA and a negative 0.5 rush WPA. And this shows that their passing game adds more win probability. For the yards gained, they gained more yards from passing than rushing, with 41% of yards gained from rushing. So for reference, the average of the league was 33% of yards gained from rushing. So they had a higher amount of rushing yards than the league average by 8. So as you can see in the middle visualization, the Colts had a larger proportion of rushing compared to the surrounding teams. And then finally, in the right side, the Colts had only slightly more pass attempts than rush attempts. And compared to the Packers and Texans in this graph, the Colts had a higher ratio of rushing attempts to pass attempts, despite the fact that the Colts have positive WPA for passing attempts and a negative WPA for rushing attempts. So in conclusion, my suggestion is that the Colts should have focused more on passing and a higher number of passing attempts because they only had a 438 win percentage. So if they'd taken advantage of their large pass WPA and spent less time on their rushing, which earned a negative WPA, they might have seen more success. So then finally, I'm going to look at the New York Jets. All right. And the Jets had a higher rush WPA than pass WPA. In fact, the rush WPA accounted for 88% of their total WPA, which is kind of crazy. And this can be seen on the graph on the left compared to the other teams as well. And for yards gained, the Jets gained only 29% of the yards from rushing, which ranks 26th in the league, despite their high rush WPA. And for attempts, the Jets spent the majority of their time focusing on their pass attempts, with only 40% of their total attempts as rush attempts. And since their rush WPA is so much higher and their rush attempts are so much lower, they should have spent more time focusing on rushing. And since the Jets only harbored a 438 win percentage as well, they may have seen more success if they had focused more on their rushing rather than their not so successful passing. So overall, the strategy of analyzing teams is kind of a case-by-case thing, and there's no overall success story that can be applied to all teams. But something to notice from the success story of the Baltimore Ravens is that Lamar Jackson is their quarterback, and he had the highest amount of rushing yards of all quarterbacks. So he accounts for much of their rushing success, and this raises the question, should teams draft more rushing-heavy quarterbacks? Also, some errors that come into account include strength of schedule, quarterback ratings, rushing and running back ratings, defensive rating, things like that. And that would also impact the strategy of the team. And then one other note I gathered from the data is that for the really bad teams, the rushing is the lesser of two evils. So the really bad teams had both negative WPA for passing and for rushing, but the rushing would be less negative. So therefore it was causing less harm than the passing WPA. And then also on average, I noticed that pass WPA is higher than rush WPA for all teams overall. And on average, teams focus more on their passing attempts and rushing attempts.
So I wanted to see the effects of how rushing and passing numbers correlated with winning. So these two graphs are very similar. Both have rushing and passing attempts in the X and Y axis respectively, and the size of the circle denotes the number of total yards the team gains. So the bigger the size, the more yards. However, the graph on the right only includes the teams that had a .500 winning record or above. On the left, we can see all 32 teams and their metrics. The two outliers are the Atlanta Falcons at near the top of the graph, who barely rushed, and the Baltimore Ravens, who barely passed. They're all the way in the bottom right. Generally, however, we see a trend with most teams clustered within 500 to 700 passing attempts and 350 to 500 rushing attempts. Now let's look at the graph on the right. As we can see, a majority of the teams are still in the same rushing and passing attempts cluster, but we can see some trends. Namely, the two teams that competed in the Super Bowl in the 2019 season, the San Francisco 49ers at around 500 rush attempts and 520 pass attempts, and the Kansas City Chiefs at around 600 pass attempts and 380 rushing attempts, had some of the most prolific offenses in terms of yards gained. However, teams like the Los Angeles Rams and Dallas Cowboys, both near the top of the graph, didn't even make the playoffs. So although having good offense is necessary to win playoff games, a good defense needs to complement it.
All right, so moving on. For my initial research, I wanted to use touchdowns as the metric to compare to the team success. And so teams with the most effective run games would typically have the most rushing touchdowns. And so the color for the graph I made, the color of each bar shows each team's point differential. And the darker the bar, like the Ravens bar, shows the bigger the point differential. I chose point differential because if you're blowing teams out more, you'd be a better team than a team that had a really good record, but they were barely winning games. And so it truly shows your strength as a team. And so as shown on the graph, two of the teams that had the most rushing touchdowns were the San Francisco 49ers and the Baltimore Ravens. And so both of these teams were incredibly successful. And as shown as the Baltimore Ravens, the color of their bar is very dark, and so is the 49ers, that they were two of the best teams in the entire league. And this was also shown in their records, as the Ravens were 14-2 and the Niners were 13-3, and the Niners ended up making the Super Bowl and losing. And on the exact opposite end of the spectrum, you have teams like the Washington Redskins, now known as Washington Football Team, and the Detroit Lions. And both of these teams had 3 wins, and they were two of the worst teams in the entire league. And part of this reason was because of their very poor rushing games. And they had many less rushing touchdowns than the league average. And then another way to measure the effectiveness of a play type is to show how often they're able to convert on the key situations of the game. And so I chose 3rd and 4th downs as these key situations, because they're typically ones that shift big momentum in the game and can be crucial to the outcome of the entire game. So as shown in the graph, teams usually pass the ball more on 4th down. However, running the ball on 4th down has shown to be more effective. This is a slightly misleading, but I think the general trend is there because many passing attempts happen when the team needs more yards to go. For example, if team is 4th and 10, most of the time they're passing the ball there, and that's a harder situation to pick up than like a 4th and 5, which is when more teams are running the ball. But the general trend of that running the ball is a more successful way than passing the ball is an interesting trend, that running is a better way to go in these situations. And then here's the graph for the 3rd down conversion rate. And so this is, the data is almost identical to the last graph, where there's a lot more passing attempts than rushing attempts on 3rd downs. But rushing the ball, even though it happens less, it's more successful to do. So it was more effective on 3rd downs than the passing was.
Awesome.
So yeah, that's it.
Yeah, great. Fantastic job, guys. I'm personally an Eagles fan, so that wasn't included, so I'm a little upset. But still, fantastic job. Again, we're going to be showing spotlights of these guys on our social media, so please look out for that. Up next is another sports-related one, but this time for, if you guys are soccer fans, this one's for you. This was a World Cup analysis of free kicks, and this is by Ben and Dylan. Ben and Dylan, which one of you guys is going to be presenting so I can give you sharing permissions? Sweet, sounds good. All right, there you go. Take it away.
Okay, let me just share screen. Yeah, so we did our project on World Cup penalty kicks, and unfortunately Ben couldn't join us, so I'll be presenting solo, but I hope you guys enjoy. So first of all, our methodology. We just did a very standard data science project, very simple. So we used pandas to analyze CSV files and matplotlib to make the visualizations. And mostly we were trying to analyze different goal zones, so like top right or bottom left, and measuring their accuracy. So these are our visualizations. First of all, the one in the bottom right is how the author of the data set kind of differentiated the different zones. So we had like this number grid. And when we did our analysis, we actually converted all of those to XY coordinates. So like the bottom left, zone 7 would be 1, 1. And first of all, the graph on the left, we measured the frequency of each zone. As you can see, zone 7 was most frequent. That was incredibly surprising because zone 7 is usually the least risky place to put the ball, so most players usually go for that. And then one of the more interesting ones was zone 3, which was top right. That was the one that people aim for the least, but as you can see in the top right graph, it was actually the one with the highest accuracy, which was interesting because we really didn't expect something with such a low chance of scoring, or such low frequency and such a high difficulty level to pull that, for someone to pull that off, to have such a high accuracy. And we kind of reasoned about it that someone who has the confidence to try a shot like that would also have the ability to execute it. So yeah, that was just a pretty interesting conclusion that we drew. The results, I mostly went over that already. Also, the average shot location was 0.92, 0.79. That would be like the bottom left corner. And as we can see, 7 was the most common. And some future work we could do, comparing right versus left footers, because that was also another data point that the author collected. And also how players aimed on the final kick of the game. It would be interesting to kind of analyze the psychology of that, because there's a lot of pressure associated with the final kick, and to see whether they would go for a safe shot or go for something really wild like top right or top left. Another thing would be to merge this with some other data sets, maybe include some domestic leagues and try to get a bit more data, because this data set was a bit limited. It was only the World Cups starting, I think 1930 was the first one. So there wasn't a whole lot of data for us to analyze. And if we had more data sets, we could have got more definitive conclusions. With that, I'll pass it back to Maxwell. Thank you all for listening.
Awesome job, guys. Thank you very much for that. Up next is a presentation on storm predictions. This is by Frank Rodriguez. Frank, the floor is yours.
Cool, thanks. Should I share permission? And I'll open it up. Great. Oh no, don't share. So, great. Can somebody see my screen?
Yep, looks good.
All right, great. My name is Frank. I'm a sophomore at Northeastern. I'm in the data club this semester, and I did a project on storm predictions in the United States. I ended up moving on a bit more towards visualizations, descriptiveness over machine learning. I'll explain a bit why later, but yeah, let's get into it. So I think that in general, for the problem statement, the importance of this, I think that we see like a lot of natural disasters and storms affect a lot of people in the Midwest, like every single day, especially in the summer. We see a lot of people frequently having to like relocate or like stop doing whatever they're doing to like make sure they're out of the way of like a tornado or hurricane, something like that. So the National Weather Service has a lot of data on these storms. They have a lot of knowledge about like where exactly they land and like how they affect people. So I wanted to try to use that data and like make sure and try to find like insights from that about where you're most likely to find these storms, and also like when you have these storms, like how big are they, like what type are they, which are like going to cause the most damage. So I think it's like probably a good thing to know, because I think that if you're not living next to an ocean and you're not ever going to have to experience a hurricane, it's probably not a good idea to sink like $10 million infrastructure into stopping a hurricane, obviously. But if you have a bit more knowledge about like what might come and when, then you can use that to inform decisions about like what infrastructure you might want to put where, or where we should try to locate people to make sure they're always going to be the safest. So the data gathering and cleaning process of this was like relatively intense, because there were 3 pretty large files that came from the National Weather Service. I initially wanted to do like forest fires in Portugal actually as my first like general thought for a project, but the data set was pretty small and also was like very limited in like range and scope. So I tried to go a bit harder here and like take these tables that were I think fatalities, the locations, and other details about the storm for the data set. Most of the details turned out to not be that important, because I think it was a bunch of like just text-based, like, oh, this happened as a description of the storm. Obviously, it's not very useful for machine learning, but there was very useful information, such as like the location, the type of storm, that was very useful to use. So in the process of this, I basically just went through and I did some just left joins on the data sets to try to get them all to come together. I think that there were about 50 to 60,000 total records of storms that we had like data on, some details, some locations, and we only had about like 500 to 600 deaths, which are the most important things I wanted to look at and see how I could try to prevent fatalities. So onto visualization and analysis. So here are the storms that we saw by location. And I think that in general, like we see like some general clustering near population centers, which I think is a bit more about the reporting, which we'll talk about later. But I think that also like the key break to this is that we see a lot of like extra storms along the coast and also in the Midwest here in the middle. So because of that, I think that we can see that like with these like different data points about where we get storms, that they're a lot more likely to like strike in like certain areas. And those are probably some of the general trends they want to try to look for. Also on these graphs, and all of them in particular, and like there are too many colors to put on like an accurate legend to make it that helpful. But the color of the storm here is just meant to be differentiating, but also these are the types of storms end up hitting. So for example, you'll see like the pink ones on the coast, those are hurricanes, or like the light blue and the purple ones, those are like thunderstorms or tornadoes or hail in the middle of the country. And this is the one that I was a bit more interested in, and it was a bit smaller and manageable to work with. So I found some fatalities like by the location and where these storms were mostly going to hit. And I found that in general, what was likely to happen is there were going to be a lot of tornado deaths in like both the Midwest and the South, which I thought was really interesting, because like I'm from Chicago in the Midwest. I am always told like if you're driving through like Illinois or Iowa, watch out for the tornadoes. But I don't hear about that when I'm going through like Tennessee or Mississippi. So I thought this is really interesting. If you see like the sizes of these dots are like proportional to like how many people like got killed in each storm. You can see there's a fairly large one in Tennessee where I think there's about like 19 deaths from one tornado. And you can see some other like relatively large like bursts across the country and throughout the South. You also see a fair amount of them that end up coming from things like hurricanes on the coast, like in Florida, by Houston. And I thought these were fairly interesting things to look at, and we could try to look a bit further from here. So moving on then from the locations into the types of storms, I thought it was interesting to like look at the different types of storms and like what was causing the most overall fatalities. And I think that clear winner here is going to be a tornado. And also the big surprising one, which I'll get to in a second, is the rip current. That also has a big effect. But I found that in general, a lot of the storms that had the biggest fatalities are probably going to be the ones that are going to be the least noticed and not necessarily the most prepared for. So obviously, like, you might get a tornado warning at some point, like maybe half an hour before a storm, but you're probably not going to have the same amount of preparation that you have like for a hurricane, where they're going to tell you days in advance. So I thought these are very interesting things, like how we can try to like use further data to prepare for these types of storms and which ones are going to be the most risky based off that. And that's how I tried to measure this here, where I tried to take the frequency of like how many times we got a measurement for a storm versus how often we necessarily saw somebody like be a victim or a fatality of that type of storm. So we can see one huge outlier on the right here is like there's nearly 20,000 records of like thunderstorms and like high winds throughout the country, but there's about 40 deaths. So we think there's like a relatively high amount of people dying from like thunderstorms or wind. But we do also think that in general, like there's going to be a lot more like recordings of those, to the point that it may not necessarily be worth trying to prevent as much if people are much less likely to die in them in like relatively smaller rates. We do also see like really high rates of death in things like there's dense fog on the coast or like an avalanche, where we only see like 5 to 20 reports of them per year, but we see significant deaths of like five deaths for dense fog with only 2 reports, or avalanches have like 20 reports, 20 fatalities. These are like really, really high rates of deaths that ends up happening. So we can like try to prevent them. We think that would be really important. Further, the one that I'm going to talk a bit more about here that I thought was a really big surprise to me, I wanted to go into a bit more depth, was riptides, because I saw it was the highest fatality, like it was the most it was like a relatively high number of fatalities, but also quite a high rate. I think that in general, anytime that we saw a rate that was anything more than like half as many fatalities as frequencies, it was a relatively small data point, as you can, or a relatively small data point, as you can see here on the graph, where most of these things on like the left near the left axis, even if they have like a very high rate, they don't actually happen that often. And I think that the outlier of this was riptides, where they were able to or where they happened only 69 times throughout the entire like data set. But we had 50 fatalities, and that was pretty high. And looking into this a bit more, what I thought was really interesting too, is that these weren't necessarily just along the coast like you'd expect. I think that we'd see that in general, of course, we'd expect that there are going to be like a lot of people dying from riptides in places like Florida or California, where they like swim on the beaches a lot. But also we see like a huge cluster here on like around Lake Michigan and like the Great Lakes area, which once again, I thought was really interesting to me, because it's like, that's where I grew up. And also in general, where it's like, even if it's not an ocean, you're still going to be like subject to a lot of these like different storms and different types of like weather fatalities that we may not have noticed otherwise. Onto the possibilities for machine learning. I ended up not pursuing much machine learning in this project because I started some and I realized that a lot of it was relatively futile, because like I said, there were over 50 to 60,000 total records. And that's not supposed to say 40K deaths, it's supposed to say like about under like 500 to 600. So the main issue with this is that any algorithm is going to end up like guessing right almost all the time, saying there's not going to be fatality or there's not going to be much damage, by just saying there's always not going to be, because the relative frequency is relatively low. So I think that in general, like if we wanted to try to explore this in the future, we could try to take like a few like specific storms that are like expected to already be the ones with the most damage and see what makes those differentiated from each other. But of course, that would take a lot of time to clean, so I didn't have the time for that this semester, but that could be an interesting extension. Further, I think the data was like relatively limited in the main way by the location. So I think that as you can see this map, we have like a bajillion data points in like the right side of the country, like throughout like pretty much all of the Midwest, South, and the East Coast. But in the West, we have like many, many less data points. And I think that sure, it's like probably some reasonable explanation that like in Nevada, if there's a desert, there may not be as many storms. But I think it's like also going to be silly to say like, oh, like all of like Nevada and Idaho and Wyoming have like way less storms than like the areas like in the states right next to them. So I think that in general, there's just like a lack of reporting of storms where people don't really live, which of course makes sense. We don't see much need to report there. People aren't going to live there. But I think that in general too, if we're trying to find like water trends, this could be still useful data to analyze. Onto the conclusion and further research, I would say that we could use like a lot of the research of the places that already had like the most fatalities in the place that we saw trends, and try to focus on storms like just specifically in those areas and not across the entire country where it's like probably going to be a ton of storms but not actually hurting anybody. And that also could be interesting to try to look at like different data sources and like different things about the weather than just like the basics of location and what type of storm it is. Like I think it will be very interesting to look at things that are going to be a lot more based on like natural features, such as like air pressure, like what wind patterns are happening, like just in general the atmosphere of a place like before a storm happens. And of course, these are things that are really hard to track over time and like track them accurately, especially because this data is like quite heavily guarded and when people want to make a profit from it. But I think that in general, if you had that data, it could be very interesting and more accurate than simply saying, oh, there's a storm here, let's see what caused it. So That was something that's very interesting. And finally, there are some like major discrepancies in how we perceive storms versus like their actual danger. So I thought like the most obvious one here was like we had like way more people like die of rip currents than hurricanes in the United States in like the 2020 data set that I used, which I thought was like a very interesting thing is that of course, like if there's a hurricane, you're going to see like a ton of like extra like news coverage about it and a ton of things like to be safe, but you're not going to hear that same amount of like warnings of just like going to the beach where you could just like die in a current. So I thought these were like interesting things where we could use like try to point out like some of these like different like weather things that we see as freak accidents that are actually a lot more common than many people might think, and use that to protect people in the future. So yeah, that's about it. I won't take questions because we're running low on time, but
yeah, that's my apologies.
Oh, of course. Thank you all.
Yeah, that was absolutely fantastic. I think the most interesting thing from that was that tornadoes occur in Tennessee. I would have never guessed that. That's absolutely fantastic. I spent a lot of time at the beach, so hearing the riptides are kind of one of the most frequent and one of the most deadly. Honestly, not surprising. It's great to see you present that, man. That was absolutely fantastic. That was supposed to be the last presentation in terms of Snowball. However, we have one more presented by Lucas, who has actually been developing since last semester and was able to come up with a presentation today. So Lucas, without further ado, he's going to be the last Snowball presentation, and then we're going to quickly go through all the vaccine data challenges and then finally announce the winners. So Lucas, take it away.
Hold on a second, sorry. Just give me a second. Can you see my screen?
Yep.
All right. Vishnesh?
Yeah, Lucas. So, hi, guys. This is Vignesh and Lucas are here. We have been working on an image recognition project, which is targeted to optimize the customer satisfaction. We are seeing a growing trend in rating the customer satisfaction to improve the sales or improve the revenue. So one such project is like a use case that we have trained us to gather the user emotions rather than filling the checkbox of multiple checkbox to how exactly the customer is satisfied with the product or with the shopping experience. So the next slide, Lucas. So we took a use case like we haven't like in our retail store which is located across the regions, and obviously we can see there is a great difference between the amount of sales with multiple regions. One such use case which we filtered out was to be the customer satisfaction, which topped most. So this led to a drastic reduction in the amount of refunds that was processed. That's probably in the next slide. So yeah, this was filtered out to study the amount of refund that was processed per store based upon the customer satisfaction, and the location which had a better satisfaction from the customers, either with the shopping experience or with the product, had a lesser number of refund compared to the other stores over to our right. And yeah, the next slide. So this is like more like a cluster behavior which we have studied across the region, and so based upon this problem statement, we had followed a paper, scientific paper, which studied about image processing to identify the customer satisfaction. We have built machine learning models to solve a problem statement. Yeah, that's the. Yeah, you can go to the next slide. I'll take over.
Sunday. So basically, this project is inspired by the real-time. This part of the project is inspired by the real-time facial expressions recognition paper by Preet James and Rupesh Acharya. I'm pretty sure I'm butchered that name. Those names, and they basically use alumni before us in 2019. And their paper, based on the paper, it basically builds three different facial emotion recognition models and decide which is the best model to use. And the idea of this project is basically when we wanted to collect the customer feedback, but usually when you check out, when you don't really push on the buttons to indicate how is the customer service. So instead of actually like doing that, we want to take a picture of them. The idea is take a picture of them and analyzing what is the emotion expressions on the person face, and then make a deductions to whether or not he or she is happy with the service that we got. And the data set is basic. The data set named for 2013 consists of 48 times 48 pixels grayscale image of faces. The faces are more or less centers, so that is occupied the same amount of space in each image. And we will categorize the facial expressions into one of 7 category, as you can see that on the left hand side in the emotions, from 0, which is angry, 1 disgust, 2 fears, and so on like that, to 6 neutral. The pixels columns has a string which is space related pixels value in row matrix order, surrounded in a code for each image, and we'll be predicting the emotion column. So the training set has 28,000 inputs, whereas the public data test set is 3,589 column, 89 volume, 89 inputs. And then after that, we're using the CNN, which is CNN is the class deep neural network most commonly applies to analyzing the visual imagery. And then after that, the VGG19, which is CNN with 19 layers. The pre-trained functions, you can find it online, in effectively used to classify image into 1,000 object categories. But this one, we decided to train it ourselves. And last but not least is the ResNet, which is basically CNN 34 layer, but there is the catch, which is introducing the so-called concept of identity shortcut connections, because the more layer that you add on into your model, the better the model predict. However, in exchange is that there's gonna be a diminishing accuracy score. So the residuals network, or ResNet in this case, actually like fix these issues by bypassing these using blockchains, the block in order to bypassing and still retaining that accuracy score. And the coding step that we basically did for each and every single one of these model is converting the lines to array as the line representing pixels, creating the train test sets, converting our training variables to in-B array, normalizing inputs between 0 and 1, reshaping the arrays to 48 times 48 constructive models, and generating batch of tensor image data with real-time data augmentations, and create the functions to read the emotions and apply it to the picture. So as you can see that like we already like from the training set. So now with the test, this is basically an image that we found online. And when we put it into the image, we put into the model will slide up the image and make the predictions that this is basically the fears, and also at the same time the percentage of how sure the model is to indicate the emotions that the image has. And then after that, we also want to set, we see that the test set accuracies rate improve from CNNs to VGGs to ResNet, which ResNet is the highest one from 63%. But the thing is that like because we kind of like having problems with dealing with ResNet given to the into the infrastructure. So we use the 63 from the previous report, whereas the VGG19 and CNN was appropriately calculated and compute. And then after that, we create, instead of using the video imagery, the video analyzing like the model suggests, like the previous paper suggests, we decided to build our own, and basically you can take the image of the person in front of the camera from the computer here, and then after that you can actually put this back to the model in order to analyzing the emotions of the image. And this is the example that I have right here for me. Thank you so much for listening to the presentations. Absolutely. Yeah.
Lucas, that was absolutely perfect. I just want to say, Lucas and Vignesh, they've been working on this project for a really long time. They've been working on it since last semester. So I want to kind of give a really quick shout out to them and all the hard work they've been doing on that really interesting project, working on ad optimization specifically for facial recognition and kind of seeing the emotions of the consumer. Again, we're going to be giving a spotlight to all these presentations, such as Lucas's. So please follow us on social media. We'll make sure we link all of that at the end, and ask any questions you guys want, and we'll make sure we get you in contact with them. Without further ado, just again, all the Snowball presentations were fantastic. Really excited to see, if any of you guys get involved next semester during the fall for these projects. Really excited to see what you guys come up with. Now to close this out, I'm going to share my screen, and I'm going to be walking through the final presentations. So just give me 1 second. All right, perfect. Can everybody see my screen?
Yeah, looks good.
Awesome. All right, now for the data challenge presentations. If you're unfamiliar, the data challenge is the vaccine data challenge, and it challenged students to visualize vaccine distribution across the United States, visualize and analyze kind of COVID hotspots, and then finally suggest a way that students or that the country needs to improve distribution to best combat COVID-19. So first starting off, Roger Meng, unfortunately, he is not able to attend today, so I'm going to be going through his slides very briefly. As you can see right here, he has hotspot plots, COVID distribution in the United States, and then kind of counters that with vaccine allocation distribution. A very clean visualization right here, very nice. And also you can kind of see a correlation between COVID distribution and how much vaccines were allocated across the United States. Right here, this plot shows the quantity of vaccine allocation each week. A surge appears in the weeks of 15th of February and 22nd of February. That's kind of as people are starting to distribute vaccines. And the second plot depicts the difference of death numbers between the 2 weeks before the surge and after. And then here are some of the results that he got. Unfortunately, like I said, unfortunately, he wasn't able to attend, so hopefully we can go through at a different time. We're going to be showcasing all the vaccine data challenges as well, so you'll be able to see this through our mailing list, through all of our socials, things like that, to get more details and to have Roger present it to you instead of myself. Now going forward, Benjamin, Margaret, and Carrie, I'm going to be scrolling through, so if one of you want to speak, and then just let me know when to hit next.
Hi, so my name is Carrie, and yes, our group is Ben, Margaret, and me. But so what our group did is we took a standardized metric called COA and DOA. You can flip to the next slide. So COA and DOA stand for cases per capita and deaths per capita over average, respectively. And so we use cases per capita or deaths per capita as opposed to just cases or just deaths, because it allows for the county populations to be factored into our metric. But so COA is the difference between a county's cases per capita against the national cases per capita. So for example, in the plot shown, whenever Texas has a higher average case per capita than the national, COA is going to be positive, indicating that they're doing poorly when compared to the US. And you can see that this is marked in red. So the expected COA can be used to find a z-score, as will be discussed on the next slide. The expected COA factors in vaccine distribution throughout the states, and this is because states that receive more vaccines should be expected to perform relatively better than others compared to the national average. And you can use the same calculations for DOA as well.
So while expected COA and DOA are useful baseline predictions for COVID cases and deaths, we need some additional context to really analyze vaccine distribution policy. So what we focused on singling out was the effectiveness of vaccine prioritization. While efficient vaccination is also really important, it's easier to find metrics like supply used on existing vaccine trackers. So since expected COA and DOA already account for vaccine numbers, any difference from the expected value can be attributed to random variance or government policy. Some of that random variance was accounted for by turning the expected COA and DOA into z-scores. And for that, the standard deviation was a pure function of population density, and this makes sense logically, since denser places have more predictable outcomes than places with people spread out more sporadically. There's a graph in the bottom right that shows a negative log linear correlation between the standard deviations of COA and DOA and population density. And the z-scores themselves are shown in the videos as the time lapse from January to March of 2021. And by looking at larger area or statewide trends, we can really start to nail down what places do and don't have effective policies. For a quick example, on the right graph, a state like Kentucky grew significantly worse in death z-score over time, and not single out. The rise could be a result of something like reopening policies. Identifying the most over and underperforming places is an important first step before case studies for evaluating which places have good vaccine distribution policies. Go to the next slide.
To illustrate the process of analyzing locations of interest, we're going to take a look at Texas as a case study. Using the metric COA, the impact of vaccine phases on the population can be visualized. This can be seen in the Texas cases graph in the top left, where the bars are the weekly new COVID cases and the line is COA. Here we can see that in late October, Texas saw a rise in cases, peaking in mid-January. In December, Texas began phase 1A of vaccine distribution, and phase 1B began shortly after. Just a month after phase 1B began, the cases began to steadily decrease. COA now indicates that Texas is performing slightly better than the other states in cases per capita. While this decrease could be attributed to many factors, vaccines certainly helped. Looking into Texas's vaccine distribution policies, we see that Texas has prioritized distributing vaccines to areas of high population density, with areas surrounding major cities receiving the most doses. It is important to target these locations as these areas have significantly more reported cases and deaths in Texas. However, a weak point in Texas's vaccine distribution is the 4 million doses that Texas has received but is yet to administer. They have used 4.8% less of their supply than the national average. As seen with Texas, some states are more efficient at administering doses than others. We can also see that some states are receiving much more doses per person than others. We propose to even this metric out by placing a cap on the current supply of vaccines per capita. This way, most states will be assured a constant influx of vaccines as long as they are distributing effectively, and the slower states will be encouraged to improve their state-level distribution practices. Overall, we plan to use our COA and DOA metrics to identify states that are doing well and learn from their practices. Thanks for listening.
Absolutely fantastic job. Thank you guys very much. Next up, we have Namrata Ray, Sanjana Ray, and Sachpreet.
Hi everyone, my name is Namrata and I'm a fourth year marketing analytics major. So going to the first slide. So we use Tableau to create our visualizations. This first slide is an overview of deaths, positive cases, and tests. And as you can see, it can be filtered by states. So the graph shows the 7-day rolling average. And the next slide is the growth by state by day. And with the more saturated sections mean that a large amount of deaths occurred during that time period. You can see it is broken down by regions such as New England, Mid-Atlantic, South, etc. The next slide is another important visualization that we created, which shows the vaccination disparity. This is calculated by the vaccination rate minus the population that are 65 and older. As of March 14th, Alaska is the only state to have vaccinated a higher proportion of its population than its proportion of individuals 65 or older, a disparity measure of positive 5%. And you can see it is green at the top. Florida has the highest population of the elderly, coming in at 21% of the population at 40.5 million people. Florida has 11.17% of the population fully vaccinated, but there's a negative 10% vaccination disparity between those fully vaccinated and the elderly, meaning there is a significant amount of elderly not vaccinated yet, and they're more susceptible to dying from COVID-19 at a higher rate than other states. We decided that the prioritization of vaccine distribution depends on the elderly population of each state, the deaths per million due to COVID-19 of each state, and the social vulnerability index, rather than the government's current plan of eligibility. Our plan will effectively detect a state's vulnerability to COVID-19. We chose 3 states as case studies to decide effective policies for states that are most similar to 3 states we selected in terms of these qualifications. Based on our qualification, we analyzed the government's response to these states based on the vaccines delivered and administered per 100,000 people and see if the ratio is effective. So one of our main solutions was to look at vaccination disparity, which is shown here. Vaccines need to be distributed to each state based on the vulnerability to COVID, as opposed to based on population. So Florida needs to have more vaccines allocated to their state. Another solution we discussed is focusing on deaths per million statistics, as well as the social vulnerability index, which is an indicator on the potential negative effects on communities caused by external stresses. The social vulnerability index ranks counties based on 15 social factors, including poverty levels, crowded housing, and lack of vehicle access. Focusing on these factors may ensure a better vaccination distribution process in the United States. Thank you.
Absolutely fantastic job. Glad to see that Alaska is doing so well right now. Sweet. On to the next one, Paxton and Justin.
Hi guys, I'm Justin and this is Paxton. Before we go on to the next slide, I can just describe a bit of how we split up our project. We kind of did two sections. The first one was modeling of the COVID-19 pandemic. We wanted a more meaningful metric to be able to base our decisions on, and we did this through a SEER pandemic model, which I'll go over in a bit. The second part of our project was more visualization organized. We did that through a Tableau dashboard, kind of displaying some of the infrastructure our country has to handle this pandemic. Yeah, so this blurry GIF is kind of showing our SEER model. So to kind of go over what SEER is, it stands for susceptible, exposed, infected, and recovered. It's a common pandemic model. It has a few different parameters such as rate of transmission, progression, and recovery. The one we focused on was transmission. Because COVID-19 was a very dynamic situation, we had 3 different surges. We had periods where people weren't wearing masks, weren't social distancing. We decided it would be best to update this rate of transmission every 10 days. That is what this GIF is showing. And that actually got us a pretty accurate base model to look at our case and death distributions as we have started putting on vaccines, which is on the next slide. Yeah, so this chart on the left is for the last few months. As you can see, around the start of March, vaccines really started to kick in once people have been fully vaccinated. It hasn't really made that much of a difference in cases, just because, as you can expect, whether you get COVID or not, it doesn't really affect basically the total numbers just with the people who we've vaccinated so far. The blue and orange lines are the amount of vaccines that have been administered. The blue line is what actually has happened. So 78% of our country's vaccines have been successfully in arms, while the others have been either wasted or held on for later usage. If you look towards the death model, which is on the right, we see the more significant impacts that vaccines have been having. This model has assumed that everybody that we have vaccinated so far has around a 4% chance of dying from COVID-19, in contrast to the 1% national average. And as you can see, this has really started to compound and have a serious impact on the number of people dying every day. And also the orange, which is again the perfect administration, you can see that by this date would have resulted in around 100 or 200 less deaths per day.
You can go to the next one. Yeah. So this is a map of the US, and we chose 3 different sort of locations, Walmart being our grocery store, CVS being a pharmacy, and then the green squares for max vaccination site. And this just shows you the distribution. And this is to really help with comparing where US population is to where people can actually get vaccinated. So it helps to actually distribute the vaccine so it can help the most people, because obviously you have the max vaccination sites can vaccinate more people per day. And we think this would definitely help get that 78% number up. And yeah, that's about it.
Awesome. Thank you guys so much. Really impressive model for the slide previously. It kind of shows the differential between without vaccinations and with vaccinations. Puts into perspective the effect that it's taking right now. Awesome job, guys. And for the next one is a presentation by Jigesh. Abhinav and Monika.
Hi everyone, I'm Abhinav. I'll be presenting the presentations from our side. So we are from College of Engineering and we are currently pursuing a master's in engineering management. And this is our first semester over here. Can you move on to the next slide? Thank you. So this is the major insights that we found via our visualizations. The eastern region of the entire US has 4.16% of the death ratio compared to the western region that is just 1.68. So there's a difference of around 2.48%. And the red color is presented as 0 to 3% of the death ratio. Similarly, the white for 4 to 7%, and the black or the gray area is around 8 to 12% of death ratios. Moving on to the next slide. Similarly, you can check how the fully and the partially vaccinated numbers are as per the entire US locations. And here you can check how Texas has been affected by less vaccination by just 12% of the entire average of fully and partially vaccinated doses. And I like to keep it brief. Yep. Thank you so much.
Yeah, fantastic job, everybody, with the vaccine data challenge. I just want to say, first off, much like Snowball, kind of exceeded my expectations with what you guys were going to come up with, seeing all the visualizations that you did. And also, for those of you who aren't familiar with what the submission criteria was, they also submitted an 8-minute video along with their visualizations. For a lot of these groups, this isn't even all of the visualizations. They had a lot more, but unfortunately, within the confines of the Data Expo, we weren't able to present them all. Similar to Snowball, we're going to hopefully get all of these to you through socials, through LinkedIn, through our mailing list, so you can see these presentations in all of their glory and really kind of utilize all the hard work that these groups put into this. Hopefully next year we can make this a little bit longer now that we have the foresight for that. And now, with bated breath, as many of you have been waiting, the vaccine challenge results. I'm going to stop sharing and I'm going to go to the results that I have on my page. The results, I'll quickly go over kind of what the criteria was. As you know, the vaccine data challenge was required, students were required to visualize where virus hotspots and distribution centers were, to analyze vaccine distribution policies and its effect on cases / mortality rates, and then finally suggest how vaccine distribution can be improved in the United States to help combat COVID-19, and how impactful such a solution would be. And so the 5 criteria for the rubric were how well was the problem addressed, how creative was the project, how useful is the visualizations and analysis that they developed, what were people who are viewing the presentation able to learn, how well was their message conveyed essentially, and then originality, you know, how unique is their presentation compared to kind of what you may see kind of in the general media. And now, without further ado, let me just pull up the presentation. While I'm pulling this up, does anybody have anything they want to add? Stash, do you have anything you want to add? Oh, and I just want to give a quick shout out to Professor Wells, Professor Flynn. Both of them were the judges for this event for the Vaccine Data Challenge. A huge thank you to you guys. Without you, this wouldn't be possible. Without your expertise and you guys' kind of knowledge of COVID-19 visualizations. Kind of community health and all of that. I really want to thank you guys very much for helping us with this.
It was a real pleasure. And if I can just say so, I was super impressed with all the presentations that I reviewed. And it's really, it's very thrilling at this moment in time when we're trying to explain complex data to folks in the media and to the general public, to see students spending so much time and effort to try to not only do the analyses, but to communicate them clearly. So I'm grateful that you're all learning and producing the kinds of knowledge that you are, and I can't wait for you to kind of get out in the world and help us to make sure that people really understand these complex systems that we're all trying to explain to everyone every day.
Let me echo Professor Wells' words of praise here, really quite impressive. I run the Global Resilience Institute here at Northeastern, and one of our sort of unofficial models is a disaster is a terrible thing to waste. Basically, when we have big disruptions and traumas, they draw our attention, but they also generate a lot of data, and that allows us to learn. And that's precisely what you've done here, and it's really extraordinarily impressive for what is probably the seminal disaster of my lifetime, and I'm a lot older than all of you. You're jumping in and doing what you've done has really been quite impressive. So I enjoyed and I learned from all of the presentations.
Absolutely. Thank you guys again so much. And thank you to everybody who presented today and submitted projects. Thank you everybody who's in attendance. I know you guys are super busy right now. And on that note, we'll cut to the chase. We're going to start with the graduate winners. We had 2 submissions for that. So the first graduate, in second place for the graduate competition is Roger Meng, who's unfortunately not here. And then the winner for the graduate presentation, I'm going by last names, is Maurya, Shah, and Pawar. Congratulations to you guys. A fantastic job. Again, we're going to be presenting all the stuff that you guys saw. Yeah, awesome. Give yourself a round of applause. As for the winners, I'll be in contact with you later to kind of work out details. As for the undergraduate winners, these is for first, second, and third place. To start with third place, we have Miller and Howard. Congratulations, guys. And for second place, we have Ray, and Nehal. And then that leaves with first place, Tam, Fox, and Morehead. Again, fantastic job to everybody. It's so fantastic to see such impressive presentations of visualizations all across the board for not only graduates, but also undergraduates kind of stepping up and also being so busy during such a difficult time, presenting about such a difficult subject. It's not easy. I'm really impressed with the work that everybody did, and I'm very excited to see how you guys are performing in next semester, and really excited to kind of give you guys the spotlight you deserve to an even larger audience. Yeah, fantastic. And with that, we are concluding this event. I'll be in contact with all the Vaccine Data Challenge winners, and I'll also be in contact with you guys, Snowball and Vaccine Data Challenge presenters, about kind of taking your projects a step further and getting them across all of our platforms.